You settle your attention downward, as if your thoughts can gently sink through the floor beneath you. You do not fall, you float, slowly, comfortably, through soil, through roots, through layers of stone stacked like forgotten pages. The ground is no longer hard. It is calm. It is spacious. It is alive in a way that moves too slowly for hurried eyes. You imagine the earth not as a ball of rock, but as a breathing body. Not breathing air, but breathing heat. A slow inhale measured in centuries. A slow exhale measured in mountains. Beneath you, far below the familiar surface of streets and fields and sleeping cities, warmth gathers in quiet chambers. These are not empty spaces. They are reservoirs of molten rock magma glowing softly like banked embers in a deep, sheltered hearth. You picture it not as fire, but as light thickened into liquid. Moving, but unhurried. Powerful, but patient. You were taught, when you were young, that the ground is stable, reliable, still. But tonight you allow a softer truth to arrive, that stillness and motion can live together. That something can appear unmoving while slowly changing all the time. The continents drift. The crust flexes. The mantle circulates heat upward in vast, looping currents. The planet is not a statue. It is a process. A supervolcano begins not with an explosion, but with accumulation. With storage. With time. Imagine a hidden bowl deep underground slowly filling, not with water, but with melted stone created by pressure and temperature so great that rock itself loosens into flow. This melting happens when mantle material rises and decompresses, or when water lowers the melting point of buried crust. It is chemistry, yes, but tonight it feels more like cooking than calculation. Heat is the stove. Pressure is the lid. Minerals are the ingredients. You drift deeper in your mind and see that these magma reservoirs are enormous compared to ordinary volcanic pockets. Not narrow pipes, but sprawling chambers that can stretch for dozens of kilometers. They grow gradually, fed by injections of fresh melt from below. Each pulse adds warmth. Each pulse changes the mixture. Silica, iron, magnesium, dissolved gases all blending slowly like colors folding into each other. Nothing rushes here. Urgency belongs to the surface world. Down below, everything is measured in long intervals and gentle persistence. You place your awareness on the idea of pressure. Not the sharp pressure of deadlines or noise, but geological pressure. The steady weight of kilometers of rock resting above a molten chamber. This weight does not panic the magma. It shapes it. It teaches it how to behave. Under pressure, gases dissolve into the melt, held invisibly like breath held in lungs. And that is when a new metaphor arrives softly. A supervolcano is not merely a mountain maker. It is a lung maker. A chamber that learns how to hold breath. You notice how comforting that feels, the idea that even the most powerful eruptions begin as restraint. As holding. As waiting. Above these chambers, the crust may slowly bulge upward by a few millimeters each year. Too small for you to see with your eyes. But instruments can see it. Satellites can measure it. The ground lifts like dough rising under a cloth. This swelling is not violence. It is preparation. Adjustment. Conversation between heat and stone. Sometimes the crust fractures slightly, making room. Sometimes it seals itself again with cooled minerals carried by hot fluids. The system is dynamic, responsive, self-modifying. Not a ticking bomb, but a balancing act. You imagine mountains now as blankets laid over warm sleepers. Thick, layered, protective. Not hiding danger, but containing energy. Mountains are often born from compression and uplift, but here they also serve as lids, keeping deep heat where it belongs until conditions change. Your breathing slows as you match the rhythm of geological time. Inhale for 4 counts. Exhale for 6. You realize that even your breath is fast compared to magma movement. A bubble of melt might take years to travel a short vertical distance. Crystals grow inside it while it waits. Minerals align like quiet architecture. Inside magma chambers, crystals form and melt and form again, recording temperature like memory rings. Zircon, feldspar, quartz, each one a tiny clock made of order. They are not in a hurry either. You begin to feel that the word giant does not have to mean loud. A glacier is giant and quiet. A forest is giant and quiet. A supervolcano, most of its life, is giant and quiet too. You picture one now not erupting but resting. A broad caldera landscape, perhaps, though you do not need the name yet. A wide basin formed by ancient collapse, now softened by time, lakes, and sediment. Grasses grow there. Animals walk there. Winds cross it without hesitation. Nothing in the scenery announces the scale of what sleeps below. And that is part of the lesson. The largest systems often look gentle at the surface. Heat continues to arrive from deeper sources, from radioactive decay of elements in the mantle and crust, from leftover planetary formation energy still leaking outward after billions of years. Earth is cooling, yes, but very slowly. So slowly that for all of human history, the difference is almost invisible. You rest with that thought. You live on a cooling ember the size of a world. Supervolcanic systems are rare not because they are fragile, but because they require very specific conditions: thick crust, abundant melt generation, and the ability to store magma without releasing it too quickly. Storage is the key. Retention is the secret. A supereruption is what happens when storage finally fails. But failure is not the right bedtime word. You replace it with release. You notice how different that feels. Release is not anger. Release is not revenge. Release is transition. For now, though, nothing releases. Everything holds. Everything balances. Melt enters. Melt cools. Crystals grow. Gases dissolve. The chamber evolves like a slow-weather system underground. You place your hand gently on your chest and feel your own breathing again. Your lungs expand and settle. Expand and settle. You and the planet share this rhythm: containment and exchange, pressure and ease. Somewhere far below, dissolved water and carbon dioxide remain mixed invisibly in molten rock, waiting for the conditions where they can separate into bubbles. Not yet. Not here. But eventually. Always eventually. You understand now that what seems sudden on the surface is usually ancient underneath. That surprise is often just long preparation finally becoming visible. The quiet giant beneath your feet is not planning. It is not plotting. It is simply following physics with extraordinary patience. And as your thoughts continue to sink like soft feathers through layers of warming stone, you begin to wonder what happens when held breath turns into rising motion, and how a planet decides it is time to speak. You continue your gentle descent, not falling but floating, as if gravity itself has softened into guidance. The surface world grows quiet above you, the winds, the trees, the small human sounds, and below, the deeper earth opens like a library written in temperature and time. The layers of rock feel less like barriers and more like blankets. Each one holds warmth differently. Some are cool and brittle, cracked like old paint. Others are dense and elastic, able to bend without breaking. You move through them in imagination the way a drop of ink moves through clear water, slowly widening, never forced. The deeper you go, the more you feel a steady increase in heat. Not sharp, not burning, just present. Like walking closer to a large oven whose door remains closed. This warmth comes from more than one source. Some of it is ancient leftover energy from when the planet first formed, when countless collisions gathered matter into a sphere and trapped motion inside. Some of it is continuously renewed, created by the quiet decay of radioactive elements embedded within rock, releasing tiny packets of heat like microscopic candles. You realize the planet has an inner metabolism. This heat does not rush outward in a straight line. Rock is a slow messenger. Instead, warmth travels through conduction and convection, two different styles of sharing energy. Conduction is the patient handoff, atom to atom, vibration to vibration. Convection is the circulating dance, where hotter, softer material rises while cooler, denser material sinks. Together they create great looping currents in the mantle, moving over spans longer than civilizations. You picture these currents like enormous underwater tides, except the water is solid rock that flows so slowly it only behaves like liquid when measured across millions of years. Solid, but not stiff. Moving, but not fast. In certain places, conditions align like the right notes in a chord. Pressure eases slightly. Temperature climbs slightly. Volatile elements, especially water, are present. And when these factors meet, rock begins to melt. Not all at once. Not completely. Just partially. Enough to create pockets of molten material between still solid crystals. This is how magma is born, not from universal melting, but from selective softening. It is like chocolate chips in a warm cookie, some parts melt first while the rest hold shape. You pause with that image, letting it become friendly and understandable. Partial melting is the rule, not the exception. Different minerals melt at different temperatures, so the liquid that forms has a different composition from the rock it came from. It becomes richer in silica and lighter elements, more buoyant, more mobile. Buoyancy is the quiet engine here. Melted rock is often slightly less dense than its surroundings, so it feels an upward pull, not dramatic, just persistent. Like a bubble rising through thick syrup. It does not shoot upward. It negotiates upward, finding cracks, weaknesses, and porous pathways. You imagine magma traveling not through giant open caves, but through networks of fractures and grain boundaries, squeezing, collecting, pausing, and moving again. Progress measured in meters per year, sometimes less. There is no hurry in geology, only direction. When enough melt gathers, it forms a reservoir, a magma chamber. But the word chamber can be misleading. It is rarely a clean, hollow space. More often it is a sponge-like region of partially melted rock, crystals, and liquid interwoven. A mush zone. A thermal neighborhood. The melt threads through it like honey through crushed ice. Storage is not a single event. It is a repeated delivery. New pulses of magma arrive from deeper sources, each one adding heat and material. Some cool and crystallize at the edges. Some mix with what is already there. Temperature fluctuates gently. Composition evolves. The reservoir matures. You think of it like a long simmering stew. Ingredients are added at intervals. Heat is adjusted from below. Flavors blend slowly. No single moment defines it, only the accumulation of many. Chemistry here is not cold mathematics. It is relationship. Silica content affects viscosity, how easily magma flows. Higher silica creates thicker, stickier magma, which traps gases more effectively. Lower silica produces runnier magma that allows gases to escape more freely. This difference will matter later, but for now it rests quietly like a seed of understanding. Gases are always part of the mixture. Water vapor, carbon dioxide, sulfur compounds, all dissolved under pressure, invisible but influential. You remember the idea of breath held in lungs. Deep underground, pressure keeps these gases folded into the melt, unable to expand. Contained does not mean absent. It means waiting. The surrounding rock responds too. Heat from the magma alters it, transforms minerals, drives hot fluids through cracks. This process, metamorphism, changes the texture and chemistry of the crust around the reservoir, sometimes strengthening it, sometimes weakening it. The container and the contents shape each other continuously. Nothing is isolated. Everything is conversation. You rest in that thought and feel how different it is from the way disasters are often described. Here, there is no villain. No suddenness. Only feedback loops and balance adjustments. Energy enters. Energy redistributes. Structures adapt. Some magma reservoirs cool and freeze completely, becoming plutons, vast bodies of intrusive igneous rock locked underground forever. Others remain warm for hundreds of thousands of years, sustained by repeated injections from below. Longevity depends on supply. Heat must be replenished, or storage becomes stone again. Supervolcanic systems require extraordinary storage capacity. Not just a tank, but a complex, multiple connected reservoirs, stacked or spread laterally, sharing melt and heat. You picture a network of glowing lakes linked by narrow channels, each influencing the level of the others. Monitoring this from the surface is subtle work. Tiny ground movements. Slight changes in gas emissions. Faint seismic murmurs. But you set that aside for now. Tonight is about formation, not measurement. You notice how comfort grows when processes are understood as gradual. Fear prefers sudden mystery. Calm prefers visible steps. And here the steps are many: heating, partial melting, buoyant rise, pooling, mixing, storage, renewal. You match them to your breathing, one step per exhale. Heating. Softening. Separating. rising, gathering, resting. The planet stores fire the way memory stores experience, layered, encoded, revisable. Each pulse leaves a trace. Each cooling margin records a boundary. Crystals grow like timestamps within the melt, capturing temperature and chemistry in their structure. Later, scientists will read them like clocks. But for now, they simply grow in the dark, orderly, and precise. You sense that storage is not passive. It is dynamic stillness, like a cat sleeping with ears alert, like a heart between beats. Energy is present, but disciplined. And somewhere in this vast underground kitchen, gases remain dissolved, pressure remains balanced, and molten rock remains mostly where it is, not because it cannot move, but because the conditions for movement are not yet complete. You drift gently beside a growing reservoir and feel its warmth without danger. You understand now that before any great geological voice is heard, there is a long period of listening, mixing, and keeping. And as you float beside these hidden stores of planetary heat, another question begins to glow softly in your thoughts: what happens when dissolved breath begins to separate into bubbles, and quiet pressure starts learning how to rise? You remain in the deep places, where warmth moves slowly and nothing needs to hurry. The magma reservoirs you visited before are still here, glowing softly in the dark like covered lanterns. They are not empty. They are not simple. They are layered mixtures of liquid rock, suspended crystals, and something more delicate, dissolved gases, hidden like secrets in a letter. You move closer in your imagination and notice that molten rock is not truly smooth. It is textured with possibility. Within it are molecules of water, carbon dioxide, and sulfur compounds, all held invisibly in solution by pressure. They are present the way air is present in your lungs, not seen, but essential. Pressure, down here, is not an emergency. It is a caretaker. It keeps gases folded into the melt, preventing them from expanding. The weight of kilometers of rock presses from above, and that steady force changes behavior. Under high pressure, gases prefer to stay dissolved. They become part of the liquid instead of separate from it. You picture a sealed bottle of sparkling water resting unopened on a table. Inside, carbon dioxide remains dissolved because pressure holds it there. Nothing escapes. Nothing fizzes. Stillness is maintained by containment. The magma is like that bottle, but on a continental scale. You let this image settle slowly. No explosions. No violence. Just chemistry responding to conditions. Dissolution is a kind of agreement between gas and liquid. Stay with me, says the pressure. And for a long time, the gases do. But conditions are never perfectly fixed. Temperature shifts. New magma arrives. The chamber grows, cools at the edges, heats again in the center. Crystals form and remove certain elements from the melt, changing what remains. With each adjustment, the capacity of the magma to hold dissolved gas changes too. Capacity is a gentle word. It means how much can be held without strain. You know this word from your own life. A cup has capacity. A schedule has capacity. A heart has capacity. Magma does too. If the melt becomes more viscous, thicker, stickier, richer in silica, gases have a harder time moving through it. They cannot drift upward easily. They remain trapped longer. This increases internal tension, though not yet release. You imagine honey compared to water. In water, bubbles rise quickly and escape. In honey, they struggle and linger. Viscosity is simply resistance to flow. But tonight it feels like temperament. Some magmas are easygoing. Some are reserved. You drift beside a region where fresh magma is entering an existing reservoir. It arrives hotter, more fluid, carrying new dissolved gases. When it mixes with cooler, more crystalline magma, the temperature contrast creates motion, slow swirling, folding, blending. This mixing can trigger new crystal growth and partial melting at the same time. Complexity increases quietly. With mixing comes redistribution. Gases move from regions of higher concentration toward lower concentration, seeking balance. But balance is rarely perfect. Small pockets become slightly overfilled. Microenvironments form where gas content exceeds what the liquid can comfortably hold at that pressure and temperature. This is where whispering begins. At microscopic scales, tiny bubbles nucleate a word that means a new phase begins. A surface appears where none existed before. A boundary forms between gas and liquid. The first bubble is extremely small, smaller than a grain of dust, but it is a turning point. It is the first syllable in a long geological sentence. You imagine it like the first star appearing at dusk. Bubble formation requires a place to start, often a crystal edge or a microscopic irregularity in the melt. Perfect uniformity resists change. Imperfection invites it. You find that comforting. Flaws are doorways. Once a bubble forms, it changes its surroundings. Pressure redistributes locally. Dissolved gas nearby prefers to join the bubble rather than remain in solution. The bubble grows, molecule by molecule. Growth is slow, but persistent. Pressure is beginning to learn a new language. You notice how different this is from the idea of sudden eruption. Here, everything begins quietly. A bubble is not a blast. It is a shift in preference. Gas deciding it would rather be free than dissolved if conditions allow. But conditions still matter. If external pressure remains high, bubbles stay small. They are compressed, contained, discouraged from expanding. If pressure drops even slightly, they enlarge. Expansion reduces density. Reduced density increases buoyancy. And buoyancy encourages upward motion. You follow a cluster of bubbles rising through viscous magma like lanterns drifting through fog. They move slowly, merging when they meet. Coalescence is their word for union. Two bubbles become one larger bubble, which rises more easily than either could alone. Small freedoms combine into larger freedoms. As bubbles grow, they change the physical behavior of the magma itself. Gas-rich magma becomes more compressible, more responsive to pressure change. It can foam under the right conditions, expanding in volume without adding new material simply by allowing gas to occupy more space. Foam is not chaos. It is structure filled with emptiness. You think of bread dough rising, of sea foam gathering on a quiet shore, of clouds forming from invisible vapor. Expansion is a common story told in many materials. The pattern repeats across scales. In a sealed magma system, bubble growth increases internal pressure if volume cannot expand. The chamber walls feel more force from within. Rock, though strong, is not infinitely rigid. It bends slightly under stress. It fractures if stress exceeds strength. But long before fracture, it deforms, stretching in microscopic ways. The crust above a reservoir can dome upward by small amounts, adjusting like fabric over a filling pillow. This deformation releases some pressure, restoring temporary balance. The system negotiates with itself continuously. You appreciate this, that Earth prefers adjustment over rupture whenever possible. Gases also change chemistry as they separate. Sulfur species may shift form depending on oxygen conditions. Water influences melting behavior around it. Carbon dioxide affects bubble growth differently than water vapor does. Each gas has personality, not emotional, but physical. Different solubilities. Different expansion responses. You do not memorize this. You simply let it feel like a gathering of characters in a quiet play. Time continues passing in long, uncounted stretches. Bubble populations rise and fall. Some collapse back into solution if pressure increases again. Not every beginning continues. Reversibility is part of nature's patience. You find that soothing nothing is forced to continue if conditions change. But if pressure gradually decreases overall, perhaps because magma rises to a shallower depth, or because fractures open above, then bubble growth accelerates. Expansion becomes easier. Gas volume increases faster than it can escape through the thick melt. Internal pressure climbs more quickly now. The whisper grows into a murmur. You sit beside this idea without fear. Murmur does not mean disaster. It means communication. The system is signaling a change in state. Physics is shifting preference again. You return to your own breath and notice how uncomfortable it feels to hold it too long. Not painful at first, just full. Then insistent. Then impossible to ignore. Release becomes necessary, not dramatic. Pressure, you realize, is simply breath held by matter. The magma does not panic. It responds. Pathways may open. Cracks may extend grain by grain. Gas may begin escaping through permeable zones, relieving tension gradually. Many systems settle this way, never erupting, simply exhaling invisibly through diffuse degassing over centuries. Release does not always mean explosion. Often it means leaking, sighing, adjusting. You let that reassurance spread through you like warmth. Still, you sense the threshold concept forming, the idea that beyond certain conditions, containment cannot continue unchanged. That bubbles, once numerous enough, change not just pressure but behavior. They connect. They form networks. They make the melt more like foam than liquid. And foam remembers how to rise. You drift in this suspended moment between containment and motion, between silence and statement, and you feel the planet holding its breath in a language made of physics, waiting for the moment when rising becomes inevitable, and the whisper finally learns how to speak aloud. You drift now not downward, but backward through time so slowly it feels like floating through dusk. The present loosens its grip. Cities fade. Roads dissolve. Forests thin into ancient ancestors. The air itself changes character. You are traveling into deep time, where the earth is familiar in shape but different in mood. There are no human voices here. No maps. No names. Only processes unfolding with patient authority. You hover above a prehistoric landscape, wide, quiet, green in some places, bare in others. The ground seems ordinary at first glance. Rolling terrain. Rivers moving in silver curves. But beneath this calm surface, one of the great magma systems of the ancient world has been storing heat and melt for a very long time. Tens of thousands of years. Perhaps more. You already understand now that nothing begins suddenly. So you do not expect suddenness. You sense preparation, the long chemistry of gathering, the physics of pressure, the architecture of stored melt and growing bubbles. The crust above has stretched, sealed, fractured, and healed many times. Tonight, you are here to witness not violence, but scale. The chamber below has reached a critical state, not emotional, not dramatic, simply physical. Gas-rich magma, viscous and buoyant, occupies a vast connected reservoir. The surrounding rock can no longer fully contain the internal pressure. Fractures link together into pathways. Pathways link into conduits. Connectivity appears like cracks in cooling glass. Failure, in geology, is not collapse, it is transition to a new structure. You imagine the first opening not as a blast, but as a door unlocking. A fracture reaches the surface. Pressure drops sharply along that path. Dissolved gases expand rapidly. Magma accelerates upward, pulled not by anger but by buoyancy and decompression. Expansion drives motion. Motion drives more decompression. A feedback loop begins, self-amplifying, but still governed by simple rules. You watch from a peaceful distance as the eruption column rises, not as flame, but as a towering plume of fragmented magma and gas. It is not burning, it is breaking. The column climbs higher and higher, pushed by thermal energy and gas thrust, punching into the upper atmosphere. You imagine it like a tree growing in fast motion, trunk, branches, crown except made of ash and vapor. Winds at altitude begin carrying fine particles outward across enormous distances. Sound would be immense here, but you are listening in silence. The scene is visual, not auditory. A moving painting of planetary force. Ash begins to fall softly at first across regions far from the vent. Tiny grains, each one a fragment of former melt, drift downward like gray snow. They settle on leaves, on water, on stone. Layer by layer, the land is rewritten. Ash is not just debris, it is future soil, future chemistry, future fertility waiting in powdered form. You kneel in your imagination and let a few grains fall across your palm. They are light, almost weightless. History can arrive gently. Closer to the eruption center, the behavior is different. When eruption columns grow too dense or lose upward momentum, they collapse under their own weight. From that collapse come pyroclastic flows, ground-hugging currents of hot gas and volcanic particles moving outward at great speed. Not lava rivers, but ash hurricanes close to the surface. You do not ride inside them. You observe from above, where their motion looks like weather roiling, expanding clouds flowing along valleys, over ridges, filling low places first. Temperature and velocity are extreme, but you hold the image at a distance, translated into shape and motion rather than danger. These flows deposit thick blankets of material called ignimbrite, welded ash and pumice that will later harden into rock layers geologists can read like chapters. Layers are Earth's memory technique. The eruption continues not for minutes, not for hours, but sometimes for days or weeks in pulses. Output is measured not in truckloads but in cubic kilometers. A supereruption releases hundreds to thousands of times more material than typical volcanic events. Not sharper, just vastly larger. Scale changes everything. A candle and a sunrise are both light, but magnitude creates different consequences. As magma leaves the reservoir, pressure inside drops. The emptied space cannot support the weight above indefinitely. The crust begins to subside. Ring fractures propagate around the chamber margins. Blocks of overlying rock sink downward in stages. This collapse forms a caldera, a broad depression rather than a steep cone. You watch the land gently fall inward, like a loaf settling after baking. Not a hole blasted open or roof lowering onto missing support. Calderas can span tens of kilometers. Seen from above, they look like basins, not mountains. Paradox appears again. The largest eruptions often leave the flattest scars. Ash in the upper atmosphere spreads across continents. Fine particles and sulfur aerosols reflect a portion of incoming sunlight back to space. The effect is not darkness, but dimming a planetary veil. Temperatures shift slightly downward. Growing seasons shorten in some regions. Climate responds not emotionally, but mathematically. You picture sunlight passing through a thinner curtain. Ice cores in your far future will record this moment as a chemical signature, sulfate layers, microscopic ash, isotopic clues. Sediments will capture it. Crystals will timestamp it. The eruption becomes not just an event, but a marker, a line across multiple natural archives. You feel a quiet awe at this, that one geological transition can write itself into so many record books at once. Life does not end. It adjusts. Some regions suffer. Others barely notice. Ecosystems are uneven in their vulnerability. Aquatic microorganisms may continue almost unchanged while large grazing animals decline locally. Variation is the rule. Outcomes are distributed, not uniform. You walk now across the landscape months after the eruption. Ash layers soften under rain. Chemical weathering begins immediately. Volcanic glass breaks down into nutrient-rich clays. Phosphorus, potassium, trace metals all become available to future plants. Sterility is temporary. Renewal is built in. Disturbance is also preparation. Small green shoots appear in protected pockets. Microbes colonize first, invisible pioneers. Then mosses. Then grasses. Succession is a staircase, and each step invites the next. You notice how different this feels from catastrophe stories told quickly. When time is stretched, events become processes. When processes are understood, fear loosens into respect. Supereruptions in deep history helped shape continental surfaces, influenced climate intervals, and redistributed minerals across wide areas. They are not frequent, separated by vast spans of time, but they are part of Earth's long vocabulary of change. You sit beside a newly formed caldera lake, steam rising gently from warm margins where residual heat still escapes. The water reflects a sky slowly clearing of ash. Stillness returns, not because nothing happened, but because happening has phases. You let your breathing match the cooling ground, slower now, steadier. And as sediments begin their patient work of covering, compressing, and preserving what has fallen, you begin to wonder how far these drifting particles travel before they finally come to rest, and how one eruption can leave fingerprints on lands that never saw the mountain at all. You remain in the softened hush after eruption, where the loudest motions have already passed and the finest journeys are just beginning. The towering columns have thinned. The ground currents have settled into layered deposits. But above, far above, another story continues quietly, almost invisibly. You lift your awareness into the sky. The tallest eruption plumes do not stop at clouds. They rise into the upper atmosphere, where winds move differently, smoother, broader, more continuous. Here, fine ash and aerosol droplets enter high-altitude highways that circle the planet. You imagine them not as debris, but as travelers, countless microscopic grains beginning a long, floating migration. Each ash particle is a fragment of former melt, snapped apart by expanding gas. Many are smaller than grains of sand. Some are smaller than flour. The smallest are nearly weightless compared to the air currents that carry them. Gravity still calls to them, but slowly, patiently, like a distant voice. Light becomes softer, more diffuse. Sunsets grow longer and redder because small particles scatter shorter wavelengths first. Blue light disperses. Reds and oranges travel farther. The evening sky becomes a painter working with extended brush strokes. You rest inside that image, a world where sunsets linger like deep breaths. Not all airborne material is ash. Some of the most climate-influential travelers are sulfate aerosols formed from sulfur gases released during eruption. Sulfur dioxide rises with the plume, then reacts with water vapor to form tiny droplets of sulfuric acid. These droplets are extremely good at reflecting sunlight. Bright mirrors at microscopic scale. Reflection is gentle, but global. You think of sheer curtains drawn across a bright window, not blocking light, only softening it. When enough aerosols spread through the stratosphere, a measurable fraction of incoming solar energy reflects back to space. Surface temperatures can cool slightly for a few years. Not ice age cold, but enough to shift growing seasons, rainfall patterns, and atmospheric circulation. Cooling from volcanic aerosols is one of the few natural processes that can counter warming temporarily. Fire creates shade. Heat creates a veil. The paradox feels almost poetic. You breathe slowly and imagine farmers in distant ancient valleys noticing shorter summers. Not knowing why. Only adapting. Planting differently. Harvesting earlier. Human history contains quiet volcanic fingerprints hidden inside agricultural choices and migration patterns. Ash that settles onto oceans carries minerals with it, especially iron. In some marine regions, iron is scarce and limits biological growth. When volcanic ash provides it, microscopic phytoplankton may bloom more strongly. These tiny photosynthetic drifters draw carbon dioxide from the air and form the base of marine food webs. So even falling dust can become nourishment. You like this, that material born from fragmentation can become food for invisible forests at sea. Travel distance depends on particle size and atmospheric height. Larger ash grains fall within hours or days, usually within hundreds of kilometers. Finer particles can remain suspended for weeks. The smallest aerosols persist for years in the stratosphere, circling the globe multiple times before settling or washing out. Time aloft is a function of size and stillness. Rain eventually gathers many particles. Droplets form around them. Condensation needs surfaces, and they fall as muddy rain or faintly acidic drizzle. You imagine a gentle rainfall carrying microscopic volcanic glass onto leaves far from any volcano, unrecognized but real. Every raindrop becomes a delivery vehicle. Ice sheets and glaciers also collect airborne ash. Year after year, snowfall traps particles in layers. Compressed over time, these layers become ice records, frozen timelines scientists can drill and read. A distant eruption becomes a dark stripe between winters, a timestamp in crystal. The planet keeps receipts. You walk in your imagination across a landscape thousands of kilometers from the eruption source. People here might never see the volcano itself. No rumbling ground. No glowing vent. Only a faint haze in the sky. Slightly muted sunlight. Perhaps a dusting on still water the next morning, like gray pollen. Connection without proximity. This is one of the quiet teachings of supereruptions. Distance does not guarantee separation. Systems are linked by circulation, air, water, chemistry. The Earth is less like a set of rooms and more like a shared bloodstream. You kneel and touch the imagined dust. It is abrasive at microscopic scale, sharp-edged shards that once flowed as liquid. Under a microscope, volcanic ash looks like broken glass sculptures, curved, splintered, frozen motion. Shape preserves violence even when landing is gentle. Form remembers process. Air travel in your modern world must account for this ash because it can melt inside jet engines and resolidify on turbine blades. But tonight you keep the focus soft, not on hazard, but on behavior. Particles follow physics faithfully. Density, drag, turbulence, all guiding their drift like choreography. Nothing wanders randomly. It only appears that way when patterns are too large to see at once. You expand your view to the whole planet wrapped in a faint, uneven veil. Not darkness, diffusion. Not silence, filtering. Climate models in your future will simulate these veils with equations, but here you experience them as atmosphere breathing differently. Breathing, you return to that word again. Volcanoes exhale material upward. The sky inhales it. Winds circulate it. Rain exhales it downward again. Cycles within cycles. Exchange without intention. You feel your own breath mirror the pattern in, out, around, return. Weeks pass. Months. The heaviest effects fade. Aerosol concentrations decline as particles settle and chemical reactions transform them. Sunlight sharpens again. Colors normalize. But traces remain in soils, sediments, ice, and tree rings. A global whisper leaves local marks. Reach exceeds origin. You understand now that scale is not only about how much is released, but how far influence travels. A supereruption is not just a place event. It is a distribution event, a planetary broadcast written in dust and light. And as the last high-floating particles continue their slow orbit above the world, You find yourself wondering what happens on the ground beneath these falling grains, how buried landscapes respond, and how life learns to begin again under a sky that once carried stone. You remain with the drifting veil in the sky, watching how the smallest particles stay aloft the longest. What looks thin and harmless from below becomes powerful when spread across the entire planet. Not powerful like a wave, powerful like a filter. A subtle adjustment repeated everywhere at once. You tilt your awareness towards sunlight itself. Light leads the sun in abundance, crossing space without hesitation, arriving at Earth in steady streams. Most days, most years, this flow is reliable. But now, after a great eruption, the path is slightly more crowded. Sulfate aerosols and fine ash float high in the stratosphere, above storms, above weather, above the place where rain can quickly wash them away. Height gives them persistence. These tiny droplets and particles scatter incoming sunlight back towards space. You imagine turning a lamp down by a single notch in every room on Earth at the same time. Temperatures respond slowly, the way oceans respond to changing seasons, with delay and memory. Land cools first, especially continents far from moderating seas. Summers grow milder. Winters grow longer. Snow lasts further into spring. Mountain glaciers gain a little more than they lose. Cooling from eruptions is not uniform. Some regions change more than others. Atmospheric circulation shifts like a rebalanced mobile, redistributing heat and moisture along new paths. Jet streams meander differently. Storm tracks adjust. Monsoons may weaken or drift. Climate is not a switch. It is a network. You walk through an imagined growing season under a volcanic veil. Daylight still arrives, but crops stretch toward a softer brightness. Photosynthesis continues, yet at a slightly reduced pace. Plants measure light carefully. Leaves are instruments. They notice what eyes ignore. A shorter, cooler summer can mean smaller harvests in sensitive regions. Not everywhere. Not always. But enough to matter historically. Tree rings from eruption years often grow narrower, thin bands marking lean sunlight. Trees keep climate journals in wood. You run your fingers across invisible rings and feel time recorded as thickness. The cooling effect depends strongly on how much sulfur reaches the stratosphere. Sulfur is the master mirror maker in this story. When sulfur dioxide converts into sulfate aerosols, reflection efficiency rises. Supereruptions can inject enormous quantities upward, far beyond ordinary volcanic events. The difference is not just scale of eruption, but altitude of delivery. Altitude determines influence. Material that remains in the lower atmosphere is washed out within days or weeks. Material that reaches the stratosphere can persist for 1 to 3 years, sometimes longer, because there is little vertical mixing and almost no rain there. Residence time becomes climate time. You float high above the weather layer and see the aerosol veil circling steadily, stretched by winds into planetary bands. It looks like breath on cold glass, thin, widespread, transformative. Cooling from volcanic aerosols has been measured after historic eruptions. Instruments show fractional drops in global average temperature, small in number, meaningful in effect. You do not focus on the numbers tonight. You feel the principle instead, energy in versus energy reflected. Balance adjusted. There is a deep calm in knowing that temperature responds to accounting. Incoming minus outgoing. Absorbed minus reflected. The planet keeps ledgers made of light. You notice another gentle effect. When the stratosphere absorbs some outgoing infrared radiation while also scattering incoming sunlight, it can warm slightly even as the surface cools. Opposite responses at different heights. Layers behaving differently under the same event. The atmosphere is not one blanket. It is many sheets. Ocean surfaces cool more slowly than land because water stores heat efficiently. This storage softens the immediate drop but extends the influence. Currents carry the signal outward like a delayed echo. Climate memory lives in water. Sea ice may expand modestly in polar regions after major eruptions. Snow cover may persist longer at high latitudes. Bright surfaces reflect even more sunlight, a feedback called albedo. Reflection encouraging reflection. Cooling supporting cooling. Feedback is not emotion. It is response multiplied. You sit beside this idea and let it feel orderly. No drama, just interaction. In deep time, clusters of large eruptions have likely contributed to longer cool intervals, especially when combined with other factors like solar variation or orbital cycles. Volcanoes alone do not create long ice ages, but they can nudge the climate system toward cooler chapters when conditions are already leaning that way. A nudge can matter when balance is delicate. You imagine ancient animals adapting to slightly altered seasons, migration timings shifting, plant communities redistributing along elevation gradients, insects emerging earlier or later. Life adjusts continuously to climate variability. Flexibility is survival's quiet tool. Cooling also changes rainfall patterns. A cooler atmosphere holds slightly less moisture. Some regions may experience drought, others altered storm frequency. Patterns, not guarantees. Probability, not prophecy. You breathe in that phrase, probability, not prophecy, and feel tension leave it. Volcanic winters, as they are sometimes called, are not endless winters. They are temporary adjustments lasting a few years to a decade at most, depending on eruption magnitude and aerosol load. The veil thins. Chemistry proceeds. Particles settle. Sunlight regains its usual strength. Recovery is built into the timeline. During the cooling phase, sunsets remain spectacular. Aerosols scatter light in ways that intensify twilight colors. Painters in some historical periods unknowingly captured volcanic skies, crimson horizons born from distant eruptions. Beauty appears as a side effect of physics. You like that optics can turn aftermath into art. You lie back in your imagination under a dimmed but glowing sky and realize the paradox has fully unfolded. Heat rising from Earth can lead to cooling at the surface. Fire can make shade. Eruption can soften sunlight. Opposites are often partners in natural systems. The veil will not last forever. Already, chemical reactions are reducing particle size and number. Already, gravity is winning tiny arguments. Already, rain is preparing to wash the lower layers clean. Cycles turn without announcement. You feel the planet not as threatened, but as responsive, capable of swings, corrections, and returns. And as temperatures slowly find their way back toward familiar ranges, and the filtered light begins to sharpen again, you find yourself wondering how living systems step forward after such dim years, how seeds, spores, and small persistent organisms prepare the ground for green return beneath skies once cooled by fire. You arrive now in the quiet after the dimmed years, where the sky has cleared and the light has found its usual strength again. The air feels washed. The winds have carried away most of their high travelers. The ground, however, still remembers. Beneath your feet lies a soft gray layer, ash-settled, compacted, slightly crusted by rain and time. At first glance, it looks empty, muted, paused. But you do not hurry your judgment. You kneel in your imagination and look closer. Recovery rarely announces itself loudly. It begins at scales that reward patience. Ash is not only residue. It is also raw material. Ground volcanic glass contains minerals locked in unstable form. When exposed to water and air, these minerals begin to weather a gentle chemical conversation between rock and atmosphere. Bonds loosen. Elements release. Nutrients appear. You picture ash grains as tightly folded packages slowly opening. Rain is the first great helper. Each drop seeps through the ash layer, carrying dissolved ions downward. Potassium, phosphorus, calcium, iron, essential ingredients for plant metabolism, enter the soil solution. What once fell as sky dust becomes underground nourishment. Time transforms texture too. Fresh ash can be sharp and loose, but with moisture and pressure it aggregates into finer, more cohesive soil. Microfractures develop. Surface area increases. Chemistry accelerates. The gray blanket becomes a growing medium. You rest with that phrase, growing medium, and feel its quiet optimism. The first arrivals are often invisible to casual eyes. Microbes, bacteria, and archaea settle or awaken. Some arrive by air. Some were already present in trace numbers, waiting through dormancy. They metabolize simple compounds, harvest energy from chemical gradients, and begin building organic matter from almost nothing. Pioneers do not wait for comfort. They create it. Certain microbes can extract energy directly from minerals, a lifestyle called chemolithotrophy, feeding on stone-derived chemicals rather than sunlight. You imagine them as tiny alchemists, turning bare substrate into the earliest threads of fertility. Next come lichens, partnerships between fungi and photosynthetic partners capable of colonizing stark surfaces. They cling to ash-coated rock, secreting weak acids that help break minerals down further. They are slow artists, painting the land with thin, living films. Symbiosis becomes strategy. Wind delivers spores and seeds. Most fail. Some succeed. Mosses often follow lichens, holding moisture like small green sponges. Their bodies trap dust and organic debris, thickening the surface layer grain by grain. With each season, the ground becomes slightly more welcoming. You walk gently across this changing field and notice variation. Depressions collect water and recover faster. Exposed ridges remain sparse longer. Recovery is patterned, not uniform. Heterogeneity is nature's preferred design. Grasses are among the first vascular plants to establish when conditions allow. Their roots are efficient explorers, threading downward, stabilizing loose layers, inviting soil organisms to gather around them. Roots exude sugars, liquid carbon, feeding microbial communities in exchange for nutrients. Cooperation runs underground. You pause and breathe with that, roots feeding microbes, microbes feeding roots. Exchange instead of isolation. Insects return alongside plants. Some arrive on the wind. Others migrate from unaffected regions. Detritivores feed on accumulating organic matter. Pollinators follow flowering pioneers. Food webs rebuild from the bottom upward, energy first, then complexity. Birds visit early, even before full plant cover returns, searching for exposed insects and seeds. Their droppings deliver additional nutrients and more seeds. Mobility makes them bridge builders between damaged and intact ecosystems. Movement accelerates healing. Larger animals follow later, when vegetation reaches sufficient density. Grazers test the new growth. Predators follow grazers. Each arrival depends on thresholds: enough food, enough shelter, enough continuity. Succession is a staircase where no step can be skipped. You sit beside a young plant pushing through ash and notice something subtle. Volcanic soils, once developed, are often among the most fertile on Earth. Their mineral richness supports dense agriculture in many regions today. The very material that looked barren becomes abundance with time and weathering. Fertility can wear a gray disguise at first. Not all recoveries are quick. Thickness matters. Where ash layers are meters deep, recolonization may take decades or centuries. Where layers are thin, recovery may be measured in seasons. Depth sets the clock speed. Water pathways matter too. Streams cut channels through deposits, exposing buried soil and accelerating regrowth along their banks. Erosion is not only loss, it is also revelation. Old soil meets new sky again. You follow a small stream in your mind and see green corridors forming along its edges, first ribbons of return across wider gray. Seeds themselves are remarkable timekeepers. Some remain viable in soil seed banks for years, waiting for the right cues: moisture, temperature, light exposure before germinating. Disturbance can trigger them. Fire-following plants exist in many ecosystems, adapted to begin after disruption. Dormancy is not absence. It is readiness stored. Fungi weave through the recovering soil, forming mycorrhizal partnerships with plant roots. These networks extend the effective reach of roots, trading minerals for sugars. Communication flows through these networks: chemical signals, stress messages, resource sharing. Underground, cooperation scales. You imagine the soil as a softly glowing web, threads linking plant to plant in quiet reciprocity. There are losses too. Some local species do not return. Some ranges shift. Extinction and migration are also part of disturbance response. You hold this gently, not as tragedy alone, but as turnover within a long continuum. Earth's biosphere is dynamic, always reshuffling composition while preserving function. Function is more durable than membership. Wetlands may form in calderas and ash-filled basins, creating entirely new habitats. Lakes appear where collapse reshaped drainage. You stand now in a meadow decades after ashfall. The gray is gone, transformed into dark, crumbly soil. Roots hold it firmly. Flowers open without memory of the sky that once darkened. Yet the minerals within them still carry volcanic ancestry. The past feeds the present invisibly. Inheritance without burden. You look across this living field and understand that geology sets stages and biology writes performances. One provides substrate. The other provides story. Neither is complete alone. And as you walk through grasses that would not exist without buried ash beneath them, you begin to wonder how scientists learn to read these layers backward, how they look at crystals and stones and recover the timelines hidden inside their silent structures. You sit now with a small stone resting in your open palm. Not heavy. Not dramatic. Just a quiet fragment of earth. In daylight, you might pass it without attention. But tonight, in this slower hour of thought, the stone becomes something else, an archive. A container of memory written in structure instead of sentences. You turn it gently in your imagination and notice the tiny sparkles inside. Crystals. Ordered arrangements of atoms that grew under specific conditions of temperature, pressure, and chemistry. They are not decorations. They are records. You realize that while ash travels and ecosystems rebuild, another story is always being written not across landscapes, but inside minerals themselves. Crystal growth is patient architecture. Atoms attach in repeating patterns, layer by layer, following rules of charge and geometry. Each mineral species has its own structure, like a preferred dance step. When conditions remain stable, crystals grow smoothly. When conditions change, growth changes too. New layers with slightly different composition form on the outside. Like rings in a tree, but made of chemistry. You hold a crystal of quartz in your mind, silicon and oxygen arranged in a precise lattice. Quartz can grow in magma, in hydrothermal fluids, in cooling fractures. Tiny impurities enter as it forms, traces of aluminum, titanium, lithium, each one a clue about the environment at the moment of growth. Impurities are not mistakes. They are timestamps. You picture a magma chamber again, not erupting, just evolving. As temperature slowly drops, different minerals crystallize at different times. This sequence is called fractional crystallization, but tonight you feel it as a cooling choir, voices entering one by one. Early forming minerals remove certain elements from the melt, changing what remains for later crystals. Order emerges from cooling. A crystal that begins growing early may continue growing through multiple stages. Its inner core forms under hotter, deeper conditions. Its outer rim forms later, perhaps after new magma arrives or pressure shifts. Under a microscope, these zones appear as bands, compositional layers like subtle contour lines. A single crystal can contain a journey from depth to shallower storage written from center to edge. You find that beautiful, a travel diary without words. Some minerals are especially valued as geological clocks. Zircon is one of them, a tiny, durable crystal that incorporates uranium atoms when it forms but strongly rejects lead. Over time, uranium naturally decays into lead at a known rate. By measuring the ratio between them, scientists can calculate when the crystal formed. Radioactive decay becomes a timekeeper. You do not need the equations tonight. Only the feeling, atoms transforming steadily, predictably, like a metronome inside matter. Each tick is invisible. The sum is measurable. Deep time becomes countable through patience. Zircon crystals from volcanic systems often survive melting events and become recycled into new magmas, carrying older ages inside younger rocks. A crystal can be older than the eruption that delivers it. Heritage inside renewal. Inheritance set in lattice. Other crystals record temperature more directly. Certain pairs of elements prefer to enter minerals in proportions that depend on heat. By measuring those ratios, scientists estimate crystallization temperatures, a technique like reading a frozen thermometer embedded in stone. Pressure leaves signatures too. Some minerals only form above certain depths. Their presence signals burial or storage conditions. Others change structure when squeezed, the same chemistry arranged differently under greater load. Structure responds to stress. Stone remembers pressure as posture. Melt inclusions, tiny droplets of trapped magma sealed inside growing crystals, are especially precious clues. When a crystal grows around a pocket of liquid, that pocket becomes a miniature sample of the melt at that moment. Protected from later mixing, it preserves original composition and dissolved gases. You imagine them as fireflies caught in glass. Scientists heat these inclusions carefully in laboratories, remelting them to analyze gas content in chemistry. From them, researchers estimate how much water and carbon dioxide were dissolved in the magma, key factors controlling eruption behavior. Breath content measured from a bubble frozen in time. The held breath you learned about earlier becomes measurable evidence. Textures in volcanic rocks also speak. Rapid cooling produces tiny crystals or glass atoms locked before they can arrange fully. Slow cooling produces larger crystals with clear faces. Mixed textures reveal mixed histories, perhaps magma stored, then reheated, then erupted quickly. Texture is tempo made visible. You run your fingers across an imagined rock surface and feel differences: smooth glassy obsidian formed from very fast cooling, frothy pumice full of gas bubbles expanded during decompression, dense welded tuff made from hot ash compacted after pyroclastic flows. Each texture is a verb turned solid. Flowing, expanding, falling, welding. Chemical zoning inside crystals can even record magma mixing events. When a hotter, more primitive magma enters a cooler, evolved reservoir, crystal rims may suddenly shift composition. Like a sudden change in handwriting, the pattern reveals interruption. Disturbance leaves signatures at boundaries. Isotopes, atoms of the same element with different weights, add another layer of storytelling. Ratios of oxygen isotopes, for example, can reveal whether magma interacted with surface-altered rocks or groundwater before eruption. Geometry becomes grammar. You enjoy how calm this reading feels. No urgency. No drama. Just careful observation assembled into narrative. Many independent clues converging toward the same story increases confidence, like multiple witnesses describing the same gentle event from different angles. Convergence creates trust. Modern tools extend perception further. Electron microscopes image crystal zones thinner than a hair. Mass spectrometers measure isotope ratios with astonishing precision. Laser probes sample microscopic spots without destroying whole crystals. Technology becomes a magnifying glass for deep time. Precision serves patience. You hold your imagined stone again and feel it differently now. Not inert. Informative. Every crystal inside is a sensor that once lived in heat and pressure, then cooled into legibility. Rocks are not silent. They are just written in a language that requires translation. Translation takes care, not speed. You place the stone down gently and look back across the recovering landscapes you visited before: meadows grown from ash, lakes formed in calderas, soils enriched by weathered glass. All of it traceable through mineral clues if one knows how to read them. And as you rest beside this quiet library of crystals and cooled melt, you begin to wonder about the great volcanic systems that still exist today, vast, sleeping reservoirs beneath familiar places, and how scientists keep listening for the smallest signs that those deep chambers are shifting in their dreams. You rise slowly above the land you know today, where remnants of ancient super-eruptions lie quietly beneath forests, grasslands, and lakes. Calderas appear as broad, sunken bowls in the terrain, not mountains to climb, but landscapes to respect. From this height, scale is apparent. You see ridges and terraces, lakes collected in depressions, forests threading the edges. Nothing moves violently here. Everything moves with quiet rhythm. You hover above Yellowstone, Toba, Taupo, names that echo past events but now speak in calm presence. The earth beneath has settled into equilibrium. Magma chambers linger kilometers below, their heat contained by the thick crust above. Pressure is high, yes, but stable. Dormancy is not absence. It is a different form of being. You imagine that the planet sleeps like you do after exertion, not unconscious, but resting while small, internal processes continue. Your attention drifts downward through layers of rock. Magma pulses slowly, moving centimeters a year, imperceptible to the casual observer. Gas concentrations fluctuate, hydrothermal fluids seep along fractures, crystals grow slowly. The earth breathes subtly here. Deep time becomes perceptible not through dramatic events, but through patient observation. Monitoring instruments extend your senses. Tilt meters measure tiny shifts in slope. GPS stations detect ground movements smaller than a fingernail's width. Seismometers feel tremors too small for human feet to sense. Gas analyzers detect variations in carbon dioxide, sulfur dioxide, and radon. Together, these tools form a gentle stethoscope pressed against the planet's chest. You listen with them in your mind. The signals are faint, rhythmic, and reassuring. Pulses from deeper layers echo through sensors like heartbeats from the Earth's interior. Long-term patterns emerge, subtle yet informative. Each tremor, each swelling, each gas fluctuation is a line of a story, not urgent, but persistent. You drift over the caldera lake. Steam rises softly from hot springs, marking where heat escapes to the surface. It is not alarming, it is evidence of continuity, of energy being released gradually rather than explosively. Hydrothermal activity sustains ecosystems, thermophilic microbes thrive, algae bloom in warm waters, and mineral deposits accumulate over centuries. Life finds niches even in places shaped by ancient catastrophe. You recognize this as a dialogue between geology and biology, ongoing, patient, balanced. You follow a subtle ridge along the caldera wall. Layers of tough, welded ash and pumice reveal themselves in cross-sections exposed by erosion. These are archives of past events. Each layer tells a story: eruption size, composition, sequence. Reading them requires calm attention, not urgency. Geology speaks softly but persistently. You imagine scientists on the ground here, walking carefully along trails, placing sensors, collecting gas samples, drilling core after core. Their work is a meditation in observation. They listen, record, wait, and repeat. Prediction in this context is not prophecy. It is probability calculated from persistent signals. Uncertainty is acknowledged, respected, and quantified. You float above a distant forested caldera edge, noting how vegetation masks subtle changes in topography. Humans often perceive landscapes as static, but underneath, heat moves, rock shifts imperceptibly, and the pulse of a sleeping supervolcano continues. You sense patience, a reminder that natural processes operate on their own schedules, indifferent to human clocks. You consider the contrast with erupting systems. Then, sudden release. Now, measured containment. The difference is in timing and connection, accumulation, equilibrium, release. Understanding the present requires both attention and reverence for the past. Water collects in depressions, forming lakes that stabilize caldera floors. Sediment slowly accumulates, reflecting the climate of each passing season. Erosion carves channels, but nothing destroys, everything is transformed. Sleep is not cessation. Sleep is preparation, rehearsal, and slow adjustment. You drift higher again, seeing the caldera from a distance. Its vastness is humbling. Scale shifts perspective. What once released unimaginable energy now simply rests, massive but still, monumental in patience. From above, fear dissolves. Awe and respect remain. The planet communicates in patterns, tremor frequencies, gas ratios, ground swelling, heat distribution. You learn to read the signs as a conversation rather than a warning. Each signal is a word, each fluctuation a gentle sentence. Silence is meaningful, so is persistence. Observation itself becomes a form of meditation. You follow a river flowing along a caldera rim. Its water reflects sunlight, highlighting contours invisible from within the trees. You settle into a quiet laboratory at the edge of a sleeping caldera. The room hums softly with computers, sensors, and monitors. You are not here to witness eruption. You are here to witness attention, the meticulous, meditative process of listening to the earth. It is a quieter practice than watching fire, yet no less profound. A scientist bends over a sensitive seismometer. The needle trembles under vibrations so small you could not feel them with your body, less than the width of a human hair. Each oscillation tells a story, magma moving subtly, gas percolating, fractures adjusting. You feel that even in imperceptible motion, the earth speaks. Next, you watch instruments recording ground deformation. GPS stations measure movement in millimeters. Tilt meters detect gentle bending. Swelling in the crust is recorded, mapped, and compared over days and weeks. Patterns appear like gentle tides. You notice the rhythm not of urgency, but of persistence. High above, gas analyzers monitor sulfur dioxide, carbon dioxide, radon, and other trace gases escaping from fractures. Levels fluctuate slightly. Some pulses are from daily temperature cycles. Others hint at deeper processes. The researchers log everything patiently. Every subtle change, every small deviation could be meaningful in the vast calculus of eruption probability. You imagine watching a volcano not as a threat but as a patient, breathing entity. Your attention stretches across time and scale. You notice that listening involves repetition. One measurement is never enough. Many measurements, over long periods, reveal the underlying narrative. Patience becomes a method, humility a tool. Models on computer screens display potential outcomes, not certainties. Only probabilities. Branches of possibility fan out like delicate tree limbs. Some lead to minor surface activity. Others suggest longer-term changes. Prediction is not prophecy. It is understanding the range of the Earth's current state and its probable evolution. You walk through a virtual simulation of the magma chamber beneath a caldera. Colors indicate pressure, gas content, and temperature. You can see potential fractures developing, paths of least resistance forming. Each simulation helps researchers anticipate how the system might respond. You sense awe for the complexity. Nothing is simple, nothing is linear, nothing is static. Sensors are positioned like a network of listening posts across the caldera. Tilt meters, GPS units, seismometers, gas analyzers, and satellite imagery combine into a symphony of observation. Each instrument adds a layer of understanding. Each signal is interpreted not in isolation but in relation to others. Science becomes a conversation with the planet, not a command over it. You move outside to a field laboratory, where scientists collect rock samples and gas emissions. They inspect mineral zoning in crystals, tiny chemical fingerprints that reveal pressure, temperature, and even ascent rate of magma. They examine past eruption deposits for signs of behavior under stress. Evidence accumulates in layers, patience translating into insight. The researchers speak softly, not only to each other but to their instruments, calibrating, adjusting, aligning. Their work is a meditation of repeated gestures, a slow dance with reality. Listening becomes an art, built on observation, interpretation, and humility. You notice that humans are attuned to scales both microscopic and vast. From tiny mineral inclusions to kilometers of ground deformation, they integrate information across orders of magnitude. They listen not only with tools but with experience and intuition, honed by decades of observation. As the day wanes, you sit on the rim of the caldera and look down at the sleeping giant. Instruments hum softly. Computers record, process, and alert. Researchers continue their patient vigil. You feel the rhythm of attention, like a heartbeat shared between human and earth. Understanding is not absolute. Uncertainty remains. But careful, continuous listening allows prediction to emerge as probability rather than fear. The Earth communicates in subtle pulses, and those who pay attention can hear its stories, even when silence seems overwhelming. You inhale slowly, matching the Earth's quiet pulse, and you realize that learning to listen is not merely a scientific skill. It is a form of presence, an invitation to align with time, scale, and the patience of nature. And as the sun lowers behind distant ridges, painting shadows across the caldera, you begin to wonder how all this vigilance will guide future generations, how careful observation today can transform potential danger into understanding, and how every quiet heartbeat beneath your feet carries messages for those willing to listen. You lift gently away from the caldera, rising above valleys, forests, and rivers, carrying with you the accumulated stories of the sleeping giants below. Beneath your gaze lies not only the land you recognize, but also layers of time, centuries of ash, millennia of soil, tens of thousands of years of volcanic memory. The planet is a vast archive, each eruption a chapter, each crystal a note in an enduring score. You drift over landscapes transformed by both fire and patience. Lakes glimmer where depressions formed in collapsed chambers. Meadows thrive over soils enriched by long-weathered ash. Forests march up slopes once barren. Every ecosystem is a dialogue between destruction and regrowth. Life is persistent, not despite catastrophe, but intertwined with it. You think of supervolcanoes as more than geological features. They are chapters in the autobiography of Earth, written in rock, ash, and sediment. Some chapters end violently, others conclude in patient dormancy. Some are written slowly in crystal lattices hidden beneath the surface. Each tells a story of energy stored, released, and ultimately absorbed by the living world above. You remember the microscopic ash riding high in the stratosphere, the sunlight filtered through veils of aerosols, and the cooling winters born from fire. You recall seeds lying dormant beneath thick blankets of gray, waiting patiently for conditions to awaken them. You feel the threads connecting each story of material, energy, life across space and time. You sense that renewal is never accidental. It is a consequence of energy cycling, matter transforming, and systems adjusting. Life answers geology with resilience, and geology records life's responses in stone. Destruction is never absolute, it is a stage in continuity, a doorway to transformation. Patterns repeat across time, collapse followed by colonization, heat followed by cooling, ash followed by green. Nature moves in rhythmic cycles, patient and unhurried. You imagine yourself walking through deep time. The air carries echoes of eruptions long past, yet nothing feels threatening. You feel reverence, not fear. Knowledge transforms anxiety into awareness. Understanding the scales of time and energy allows you to observe without panic, to see the planet not as fragile, but dynamic, responsive, alive, and patient beyond human lifespans. You reflect on the scientists who observe these processes today. Their instruments and measurements extend human perception, bridging the gap between immediate experience and deep planetary rhythms. By listening attentively, by recording patiently, they translate subtle signals into understanding. They remind you that awareness, curiosity, and care are as essential as data. Science, in this sense, is a form of meditation, deliberate, slow, and profoundly respectful of what unfolds over time. Above, the clouds drift softly. Light scatters through thin layers of atmosphere, a reminder that even the sky carries memory of volcanic particles, of climatic shifts, of the ongoing dance between energy and matter. You feel a connection between your own rhythm and the pulse of the planet. Breath becomes parallel to tectonics, attention becomes analogous to seismic monitoring. Each inhale, each exhale, a subtle echo of processes far larger than your body. As you descend toward the present once more, you see the earth through new eyes. The landscapes are familiar, yet each valley, each ridge, each lake holds evidence of past forces, supervolcanic, tectonic, climatic, shaping life and its environments over eons. You perceive continuity in change, permanence in impermanence, and memory in every mineral, every crystal, every soil horizon. You rest briefly over a caldera lake, letting the reflection of the sky shimmer on its surface. You think of how deep time coexists with fleeting moments, how a single eruption can ripple through centuries of climate, how microscopic ash can nourish life thousands of kilometers away. You sense the interconnectedness of all scales, atom to mountain, season to millennium, breath to eruption. And now, as your attention returns to the familiar present, you carry a sense of calm understanding. The world is vast, energetic, and patient. Supervolcanoes remind you that disruption and renewal are inseparable. Life persists because the planet allows it, because energy is redistributed, because time is generous. You feel part of a story that began long before you and will continue long after, a story where curiosity and care allow consciousness to appreciate the subtle rhythms of a restless yet enduring earth. You inhale slowly, letting the memory of ash, crystal, and dormant magma settle like soft sediment in your mind. You exhale, releasing tension and embracing continuity. The planet's autobiography continues, written in stone and life, in heat and silence, in eruption and calm. And as the last light of imagination glimmers across your inner vision, you wonder, what will the next chapter hold, and how will those who come after you listen, interpret, and breathe with the earth as patiently as it breathes with them?